number 23, I know it had a drawing like this, where you've got a thing on a rope and it's spinning around. I think it just gave you the radius, is that right?
Yes.
So what was the radius in that problem?
0.7.
0.7, okay. Okay, and so the question is, what's the minimum velocity that you can have to get the thing to go all the way around the loop without that happening, or without that happening, right? In other words, maintaining tension in the rope, right? Okay, so look, you guys, if I spin it, the faster I spin it, the more tension there is, right? Does everybody agree with that? And as I spin it slower and slower and slower, the tension decreases, right? What's the least tension I could possibly have?
That one.
Give me a number.
0.
0. Isn't that the smallest tension I can have? Right? So look, as the thing spins around, there are two forces contributing to the centripetal force. There's gravity and tension, right? Okay? So, if my tension is 0, my smallest centripetal force that I can have and still have the thing going in a circle is if my centripetal force equals gravity, right? In other words, if our tension is 0, then our centripetal force must be provided by gravity. Let me pause there for a minute. That's a big, important idea. Does that make sense? Yes.
What's the horizontal?
There is no horizontal force.
What is that for horizontal?
Say that again.
Like this is gravity, the vertical, it's the horizontal.
Oh, do you mean like if I spin the bee this way?
Yeah.
Tension.
Okay.
Just tension. Does that make sense, Sarah?
Yeah, thank you.
Everybody? Okay, so, well, if that's true, well, then look what happens. Centripetal force is mv squared over r, right? And force of gravity is mg, right? And what happens? The m's cancel. So basically what we're saying is our centripetal acceleration, v squared over r, has got to be g. Does that make sense? All right, this is like, I can totally see this being a multiple choice question on a test. Okay? So we know our velocity, or we're looking for our velocity, we know the radius, we know g, right? So v squared over our radius, which was 0.7, has got to equal 9.8. And you solve it. Does that make sense, you guys?
Yeah.
Okay. There's another problem that was really similar to that. Somebody came in and asked me about it. Josh, what was the one you were asking about the hills, where the hills went up and down? You asked me this morning, and I directed you at this, and you're like, oh, it's the same thing?
Yeah,
15. Did you guys figure out number 15?
Yeah. Did I get? Yes, I did.
How many of you struggled with 15? 2, 3, okay. All right, so let me just say this about 15. All right, so imagine you've got a roller coaster or a road or whatever that's got two hills. One hill goes this way, one hill goes this way. Okay? So it's a car in the problem, right? It's not a roller coaster, is that right? So this is number 15. Does it give you the radius of the curve, is that right? 250, is that what you're saying, Sarah? So the idea is, am I remembering this right? Is this setup right? I can't find my copy of the sheet. It's buried on my desk somewhere. Is this one also 250? Or does it not talk about the second one? Okay. All right. So you guys have all been on roller coasters, yes? Okay. So think about just like a simple wooden roller coaster. When you go over to the top of the hill, don't you feel like you're being lifted up off of your seat? Okay? Because think about what's happening there. What's happening is, as you go over the top of the hill, your path is circular, right? And so there has to be something pulling you down. Well, gravity does some of that, but if the centripetal acceleration produced by this curve is more than gravity, then that's where the lap belt comes in, right? right? You float up a little bit until you hit that lap belt, and then the lap belt pulls you down. So now you've got two downward forces on you, right? Gravity plus the lap belt pulling you down, right? Does that make sense? All right, so at what point do you leave your seat? Like, what's happening when you leave your, like, why do you leave your seat? What would be true about the engineering of the ride to make that happen? Right words, wrong pointing. So what you just said was the centripetal force is greater than the force of gravity. So what's wrong? Why am I saying wrong pointing?
Because then you'd be flying.
There is nothing pushing him up. All right? So when you say the centripetal force, let's suppose you suppose you go over the top of this hill at 20 meters a second. Cool? So let's suppose that the velocity here is 20 meters a second. Okay? Oh, well that means centripetal acceleration is v squared over r, right? So 400 over 250 gives you 40 over 25 is 8/5 is, what, 1.6? No, 10.6? How about 16? Good? All right, does everybody see what I did there or no? Is my math right? Is it 16? You guys are useless. Is that right? Oh. Oh, it's clearly not 16. It is 1.6. Damn it. Shoot. Sorry. I'm trying to get something bigger than 9.8. 30, 40. Let's go.
12,000 meters per second.
Hang on. Sorry. Thank you. Bear with me. 1,600. I'm being stupid. All right. All right, hey guys, listen please. All right, sorry. So this is a ridiculous roller coaster, but bear with me. All right, so suppose you go over the top of it at 60 meters a second. This is going somewhere. Are we good? So you're going to get v squared, which is 3,600, over your radius, right? Am I good now? All right, so divide that out, and it gives you some big number. Is it 14.4? All right. All right, so there's a lot of work to get to what I was trying to show you here. All right, so look, there's something important about this number. It's bigger than 9.8, right? So the idea is, in this example, gravity alone is not enough to prevent you from going off of the... Gravity alone is not enough to provide the force to get you to go around this curve. Does that make sense? So what if this was a car, just like a regular car driving, it would jump. It would literally leave the road, right? Because gravity wouldn't be enough to make it accelerate at this rate. Okay? So that's why roller coasters are secured to the track, right, by wheels above and below, and it's why there's a lap belt, right? Does that make sense? Okay? So the point, what I was trying to get at, is the point at which your car leaves the road, or the point at which your butt leaves the seat, is if your desired centripetal acceleration is bigger than gravity. Make sense? So, 15 says, what's the biggest velocity you can have when you go over the top of the hill without the car leaving the track, right? So it's literally the exact same as this one, right? You just figure out what velocity will make your centripetal acceleration 9.8. And that's it. Does that make sense, you guys? Sorry, long way to get there. Good with it? All right. Is that all 15 asked? Or was there more to it? Trying to find my copy of the sheet. Just find the speed? Okay. All right, what are the ones you guys want to look at? There it is. Yeah. Yeah. 16. Oh, 16. Did you guys see the remind? I sent out a remind on 16. The answer is